let's do a couple of examples using electric current. Let's say that we have a wire and we hook it up to a battery and we got electrical current flowing through the wire here. And let's say that we measure that current to be 121 milliamps, and we have this thing going for a time of 35.1 seconds. And I want to know the number of electrons that pass through the wire as we've got it connected. Actually, the way I've drawn it, the electrons really going that way because current is going this way. Current actually moves opposite the way electrons go because we define current to be the flow of positive charge. Okay, so Q is going to be I times T, okay, and so that'll be equal to 0.121 amps times 35.1 seconds, and so the total charge there is going to be equal to 4.25 coulombs. Well, the number of electrons is going to be the total charge divided by the fundamental constant, because the fundamental charge here is in fact fundamental. That's the charge in an electron. And so 4.25 coulombs, 1.602 times 10 to the minus 19 coulombs per fundamental charge. And so that would give us 2.65 times 10 to the 19th electrons. Now, as I said, the electrons are actually flowing in the opposite direction of the electrical current. So I suppose you could say that if it's really electrons flowing, then we could make most of these negative. I kind of get a little bit sloppy with that, I admit, but that's an example here. Okay. So let's do another example. Okay, so let's do a little bit more complicated example then. So for my own background, astrophysics, we can look at the Earth here. And so there's the Earth, and we got the sun here, and we got charged particles from the sun, and they're impinging on Earth's ionosphere. Okay, and so actually it's a lot more complicated than that. They actually hit Earth's magnetosphere, and most of them go around, but we have these charged particles coming in, so we're going to ignore that for the moment and say that as the solar wind is running in towards Earth, we're going to say that the solar wind corresponds to 3.7 protons per cubic centimeter. That's the density of it, okay? And let's say that the solar wind is moving with a velocity of 540.5 kilometers per second. And so I want to know what's the current, the electrical current from the sun impinging on Earth. Okay, so let's think about that a little bit. Okay, so we want to do a couple of unit conversions here. Okay, put this all SI. So the velocity 545 kilometers per second. Okay, that's going to be 5.405 times 10 to the 5th meters per second. We had 3.7 protons per centimeter cubed. So we know that 100 centimeters is the same as 1 meter. So 100 centimeters divided by meters is a weird way of writing 1. We cube that. The centimeters cubes multiplies times that, and we get that this is 3.7 times 10 to the 6 protons per cubic meter. Okay, so how does that help us? Well, physics 1, you realize equation of continuity for fluids. Okay, so as you've got a flow rate here, then the amount per volume per time. So the volume per time, the rate is the area of the thing times velocity. Okay, so again, this is from Physics 1, from the chapter that you did on fluids. Okay, and so that means that if you get charged particles running into Earth right here, then the area is going to be the cross-sectional area of the Earth. So that's going to be pi r squared. So that would be pi r squared times the velocity. Well, that's the volume per second coming in, okay? And so if we get the volume per second coming in there, okay, then we look at that and say, okay, so that's going to be equal to pi, okay? The radius of the Earth is 6.371 times 10 to the 6 meters squared, and that's going to be 5.405 times 10 to the 5th meters per second, and so R comes out to be so R comes out to be 6.95 times 10 to the 19th cubic meters per second. Okay. So that 6.95 times 10 to the 19 cubic meters per second, okay, and that we just calculated that there's 3.7 times 10 to the 6 protons per cubic meter. So if we take that and we multiply by 6.95 times 10 to the 19th cubic meters per second, that gives us 2.57 times 10 to the 26 protons per second. And really, I suppose if we want to keep this to the proper number of significant figures, that'd be 2.6 times 10 to the 26 protons per second. Okay, well, we know the charge of a proton. So that if we want to find the charge per second, in other words, we want to find the amps, so that'd be coulombs per second. What we do is we take 2.6 times 10 to the 26 per second, okay, times 1.602 times 10 to the minus 19 coulombs per proton, okay, and that comes out to be 4.1 times 10 to the 7 amps, or in other words, 41 mega amps. That's the current impinging on Earth due to the solar wind. Okay, well, the solar wind actually varies, from day to day and with solar activity. So on a particular day, like the example, it'd be 41 mega amps impinging on Earth from the sun. And there are other factors that come into this. So this is a very, very simplistic explanation. Completely ignores the effect of Earth's magnetic field. Okay, so I guess this might actually be a little bit closer to being accurate for Venus, which actually lacks a magnetic field. But it is just kind of an example sort of problem here.